All right, we're now going to start looking at the idea of having a limit as x approaches infinity or as it approaches negative infinity. So the limit as x approaches infinity of some function f of x equals L is going to be the way we denote the idea that we can make our y values arbitrarily close to this, whatever this L is, by taking a large enough x, so as x goes to infinity. If we say that the limit as x approaches negative infinity of f of x equals L, then again that means our function values, our f of x values, our y values, whatever you decide you want to call them, can be made arbitrarily close to L when x decreases without bound, in other words, when x approaches negative infinity. In either event, the line y equals L is called a horizontal asymptote. So we've seen vertical asymptotes before. Those are the up and down ones. We also have horizontal asymptotes, which kind of go left and right. This is sometimes referred to as the end behavior of a function. All right, so let's look at this example here. When we look at the x-axis and we keep going as far as we can negative, we notice that our f of x values get closer and closer to negative 3. Now this horizontal asymptote here is kind of showing us and denoting that we're going to actually quite reach negative 3, but we'll get as close as we can. So we would say that the limit as x approaches negative infinity of this function f of x would be equal to negative 3. So you'll have a horizontal asymptote at y equals negative 3. So this line y equals negative 3 will kind of denote that horizontal asymptote. Now as we look over here on the right, we're getting as close as we can with our y values to 7, but we've actually reached there. So here we would say that the limit as x approaches infinity, this f of x equals 7. So we have another horizontal asymptote at y equals 7. So again, we just want to make sure we're understanding the difference between our vertical and our horizontal asymptotes before we get much farther. Vertical asymptotes are going to be x equals something, so maybe x equals c. And that's something where you've got an up and down line that you're looking at. And when we say we have the limit as x approaches c of f of x, if this is positive or negative infinity, this is where we have something that will have this vertical asymptote for. So f of x cannot cross a vertical asymptote. And it can have infinitely many of these vertical asymptotes. So we can have as many vertical asymptotes as we happen to have discontinuities. So say we've got some function, maybe it looks something like this. Maybe it goes down again, get another of these asymptotes. Maybe it keeps going like this. Maybe it has another one of these asymptotes, and maybe it just keeps kind of continuing in this pattern for a while. So this is the idea of vertical asymptotes, is they're just these up and down lines, and you can have as many of them as have discontinuities. However, when we're talking about horizontal asymptotes, these are of the form y equals L, and this is what happens when we have a limit as x approaches positive or negative infinity of the function equals some value L. Now it is possible to have something where this isn't a number and we just don't have a limit. Maybe it blows up to infinity or it becomes negative infinity. Then we wouldn't have a horizontal asymptote. But if we do approach some value, then we'll have a horizontal asymptote. Now, unlike vertical asymptotes, f of x can, it won't always, but it can cross its horizontal asymptote, or asymptotes. And f of x can have at most two of these horizontal asymptotes. So it can only have one when you're approaching negative infinity and one when you're approaching positive infinity. Maybe they're the same, but they don't have to be. But that's why it's at most. So we could have one where maybe this is our negative infinity as x approaches negative infinity asymptote. Maybe our function's going that way. Maybe it goes a little bit up and down, up and down. It's doing an up and down thing. And then as we're approaching positive infinity, maybe it's got another one over here that it's kind of hovering around. So there we only have two possibilities for the horizontal asymptotes. Or we can only have at most two horizontal asymptotes. Now we want to talk about how algebraically we can find these limits. So for example, say we wanted to find the limit as x approaches infinity of 1 over x and the limit as x approaches negative infinity of 1 over x. Well, the limit here as x approaches infinity of 1 over x, the idea behind this is that we're going to take 1 and divide it by a larger and larger and larger and larger number until eventually we divide it as far as we can and we end up getting 0 for the limit. So we keep on taking the 1 and dividing it up into smaller and smaller and smaller things. The same is true of the limit as x approaches negative infinity of 1 over x. This will also be 0. And so again, the same idea, even though we're getting a negative number, large number that we're dividing by, we're still taking this fraction and making it smaller and smaller and smaller and smaller and smaller in magnitude to a point where it's getting closer and closer to 0. So that would be the limit as x approaches either infinity or negative infinity of 1 over x. So we can kind of create some basic limits when x approaches, or when x approaches infinity or negative infinity. So assume that n is greater than 0 and c is a non-zero real number. So assume n we're going to use for our exponents, so keep assuming we have positive exponents, and let c be something that isn't 0. Then the limit as x approaches infinity of c over x to the n is going to be 0. So the idea is that we're taking our c, whatever the number is, and we're dividing it up into an infinite number of pieces. No matter what we have, as long as our power is greater than 0 for this exponent, we're just going to eventually get such a large number in the denominator that keeps growing and growing and growing that it'll take whatever our number is and keep shrinking and shrinking and shrinking and shrinking and shrinking it. And the same is true for the limit as x approaches negative infinity of c over x to the n. This will also be 0. Again, just no matter what the number here is, we're just going to keep shrinking and shrinking and shrinking and shrinking it. Okay, now what happens then when we want the limit as x approaches infinity of c times x to the n. Well, then here we'll end up getting one of two things. It'll be infinity if c is larger than 0, and negative infinity if c is smaller than 0. So in essence, if we've got this positive number that we have here, then we're going to just keep having it grow, times positive number will be positive. And again, this is a positive number, they'll keep growing and growing and growing. If we multiply it by a negative, we get negative infinity. One other thing I want to point out here about n, I want to have n be a natural number. So 0, things like, not 0, but 1, 2, 3, 4, 5, so on and so forth. Some weird things start happening if we start allowing fractions. So for example, you can't take the square root of a negative number. So you have to be a little bit careful about that for some of these negative limits. Alright, now when we get into the limit as x approaches negative infinity of c times x to the n, this is a little more complicated still. Because not only do we have to worry about the sign of c, but we also have to worry about whether or not we have an even or an odd exponent. So it's going to be infinity if one of two things happens. If c is greater than 0 and n is even, then this negative number raised to an even power makes it positive, and c is positive, so positive times a positive gives us a positive infinity. If c is less than 0 and n is odd, then both of these terms will be negative, and so a negative times a negative will give us a positive. And of course, if for whatever reason the signs don't match on the c and the x to whatever power it is we're working at, we'll get negative infinity. So this will happen when c is greater than 0 with the exponent being odd, and when c is less than 0 but the exponent n is even. So again, when c is positive but n is odd, then we have positive times a negative, so that's negative infinity. And when we have c is negative but n is even, so this is positive, negative times a positive will be negative. So note that not every function is going to have a limit at infinity or negative infinity or even just 0. There are other possibilities that we could get besides those three. We also might not have just those limits at all. For example, the function y equals the sine of x does not have a limit as x approaches infinity or negative infinity. And so the reason for this is if we look at our sine function, sine will always go up and down. So we've got kind of a curve that looks like this, and it keeps repeating on either side. Technically, I should start curving that at this point. And so here it's just going to keep oscillating between -1 and 1. So the limit as x approaches either positive or negative infinity of sine of x does not exist because it never levels off. This is a D for does not exist. Now, other fractions and other functions we look at are going to have some little bit stranger horizontal asymptotes to find. So say we wanted to go ahead and find the horizontal asymptotes here. If we plug in the limit as x approaches positive or negative infinity, we're going to, in the end, if we call this f of x of f of x, we're going to get infinity over infinity. Now, if we have infinity divided by infinity, this is one of those indeterminate forms that's not going to help us out. So we can't change this in any way besides adding 0 or multiplying by 1. So that would be ways that would keep this the exact same as it is. So what we're going to do is we're going to multiply the numerator and denominator by the reciprocal of x raised to the highest power of the denominator. Circle that because that's kind of our big idea here for how we're going to find these in the future. So say we have the limit as x approaches positive infinity of 3x squared plus 20x divided by 4x squared plus 9. The highest power of x in the denominator is going to be x squared. So we'll multiply the numerator and denominator by 1 over x squared. When we distribute this through, we'll have our limit as x approaches infinity of 3x squared over x squared plus 20x over x squared divided by 4x squared over x squared plus 9 over x squared. If we simplify this, we end up with the limit as x approaches infinity of 3 plus 20 over x over 4 plus 9 over x squared. And at this point, we can go ahead and use these basic limits at infinity that we have from above in order to plug in. So we know that if we take the limit as x goes to infinity of this, we'll end up getting 0. And if we take the limit as x approaches infinity of this, we end up getting 0 as well. And so we end up with 3 plus 0 over 4 plus 0, or 3 over 4. Now notice that if we go ahead and try to find the limit as x approaches negative infinity here of this same function, we'll get to this point again as well. So we'll have 3 plus 20 over x over 4 plus 9 over x squared. And again, when we do this, this will go to 0, this will go to 0, and we'll again be left with 3/4. So we only have one horizontal asymptote. So our horizontal asymptote is y equals 3 over 4. So that would be the one horizontal asymptote that we have for this problem. So let's get a little more practice with some of these limits at infinity. Say we want to evaluate the limit as x approaches infinity of 9x squared plus 4 divided by the square root of 36x to the fourth plus 7. So here, it's kind of hard to tell because of the square root, but the highest power in the denominator will be whatever x to the fourth square root of that is, which would be x squared. So what we'll do is we'll start off by taking and multiplying by 1 over x squared in both the numerator and denominator. But we'll have to think of this in the denominator as being the same as the square root of 1 over x to the fourth. The reason for that is that'll allow us to go ahead and combine it underneath the square root. So then we should get the limit as x approaches infinity of 9x squared over x squared plus 4 over x squared divided by the square root of 36x to the fourth over x to the fourth plus 7 over x to the fourth. If we wanted to continue this, we'll have our limit as x approaches infinity of 9 plus 4 over x squared divided by the square root of 36 plus 7 over x to the fourth. Again, if we go ahead and take a moment to plug in our x now, this part will go to 0, this part will go to 0, because when we take each of these fractions and we're just dividing by larger and larger numbers, they go to 0. So we end up with 9 plus 0 over the square root of 36 plus 0, which will give us 9 over the square root of 36, which will give us 9 over 6, which is the same as 3 over 2. Alright, now some of these limits that we're going to look at are a little trickier than what we've seen so far. So say we want to go ahead and find the limit as x approaches infinity of x squared minus x. This would normally just be infinity squared minus infinity, which would be infinity minus infinity. This is an indeterminate form. Since in the end, if we're taking infinity minus infinity, we don't know which infinity is bigger. So what we'll do is we'll go ahead and factor, do a little bit of algebra here. The limit as x approaches infinity of x squared minus x is the same as the limit as x approaches infinity of x times x minus 1. And now if we plug in, we'll get infinity times infinity minus 1, which will be infinity times infinity, which is just infinity. Technically, you could also say the limit does not exist here, but it does help us determine that we are increasing with this. Alright, so one that's maybe a little bit more complicated, if we have the limit as x approaches infinity of the square root of x squared plus 1 minus x, if we did this, we would get the square root of infinity squared minus 1, plus 1 minus infinity, which will again be infinity minus infinity, so this is indeterminate. So we have to go ahead and do a little bit of algebra here. When we see a square root minus or plus something, we should multiply by the conjugate. So this is kind of an older trick we haven't seen in a little bit. But the idea is we'll take the square root of x squared plus 1 minus x over 1 and multiply it by this term, with the minus switched to plus in the numerator and the denominator. So the conjugate will be this thing I'm writing here in red, which will be the square root of x squared plus 1 plus x over the square root of x squared plus 1 plus x. The reason we have to do this is that by multiplying the numerator and the denominator, this is essentially multiplying by 1. And by switching the sign, what we'll get is the middle terms in our foiling process will cancel out. And so what we get, after we FOIL together, will be the limit as x approaches infinity of x squared plus 1 minus x squared over the square root of x squared plus 1 plus x. Now, canceling out in the numerator, we have the limit as x approaches infinity of 1 over square root of x squared plus 1 plus x, which this is all positive, and so all of these terms will just keep increasing and increasing and increasing, so we end up with an answer of 0. All right, for another one that'll be a little bit to think about, if we have the limit as x approaches infinity of sine of 1 over x, note that sine of x didn't have a limit. But here we can think about this as being the sine of the limit as x approaches infinity of 1 over x, which is the sine of 0. And we know the sine of 0. The sine of 0 is just 0. So a little bit to think about with that one, but we can move the limit inside instead because it's not really applying to the outside part of the sine. And that allows us to see we just have the sine of 0. All right, a few more. Maybe just a couple. We have the limit as x approaches infinity of x squared plus x over 3 minus x. The highest power of x in the denominator, not overall, just the denominator, is x. So what we'll do is we'll multiply the numerator and the denominator both by 1 over x. This will give us the limit as x approaches infinity of x squared over x plus x over x divided by 3 over x minus x over x. When we cancel out each of these things, we'll have the limit as x approaches infinity of x plus 1 over 3 over x minus 1. Plugging in the limit now, plugging in infinity, we have infinity plus 1 over 0 minus 1, which will be infinity over negative 1, which is negative infinity. Again, you could technically say the limit does not exist here, but that negative infinity helps us know whether or not we are increasing or decreasing. So some things to note about these limits towards infinity with these different powers of x. If we don't have square roots that are causing weird things to happen, if we have the same highest power of x in the numerator and the denominator, the limit will be the ratio of the coefficients of the highest powers of x. If you have a higher power of x in the denominator, the limit will be 0. Essentially, if you have numbers getting larger and larger and larger more quickly and you're dividing by those things, your limit will be 0. But if your highest power of x is in numerator, then the limit will be positive or negative infinity, and that'll just play out based on what the other things around it are. So if we're just dealing with x's and different powers of x's in the numerator and the denominator, these 3 rules will help us kind of see what that limit should be at kind of first glance. Now again, you don't know if it's positive or negative infinity, so you have to do a little bit of work to figure out which way it's going, but it at least will narrow it down for you. Alright, so now say we wanted to find the limit, the horizontal asymptotes of g of x, which is the arctan of 7x cubed minus 6x plus 3 divided by x squared plus x. What we'll do is we'll take the limit inside first. Note that arctan of x is the inverse tangent. And it's not the same as 1 over the tan of x. Something that's confusing about this is that in other places, instead of seeing arctan, you might see tan raised to the -1 of x, but that is not the same as 1 over the tangent of x. So note, sometimes, and even on calculators this happens, denoted tan inverse of x, which can be confusing. And the same thing will happen with sine inverse and cosine inverse. It's a little nuts. I mean, even on, I don't know if you can see on my calculator, but if we want to go ahead and find the sine inverse, cosine inverse, and tan inverse, technically these are arctan, or arcsine, arccosine, and arctan, which is not the same as 1 over. So it's a very confusing point in the terminology. So just be a little bit careful. When we take the tan of some value, we're saying if I plug in an angle for x, I should get out some value for the tangent, which will be a ratio of the opposite divided by the adjacent side. However, if I'm saying arctan of x, x is that ratio, and I'm using it then to try to figure out what the angle is. So just be careful about all these things. So that's a little bit of a side, well, tangent, for lack of a better word. If we want to take the limit as x approaches infinity of just the inside part, so we know what we're dealing with, we'll have 7x cubed minus 6x plus 3 over x squared plus 10. Now again, we want to take this and multiply by 1 over the highest power of x in the denominator, so that'll be times 1 over x squared divided by 1 over x squared. When we do this, we get the limit as x approaches infinity of 7x cubed over x squared minus 6x over x squared plus 3 over x squared divided by x squared over x squared plus 10 over x squared. Now you might be wondering, Mr. Smith, why aren't we just using the rules we have from up there? Don't we know that this is going to be infinity because the power in the numerator is higher than the power in the denominator? Well, yes we do, but I wanted to make sure we played it out, showed it out why that ends up working that way. When we cancel things out, we have the limit as x approaches infinity of 7x minus 6 over x plus 3 over x squared divided by 1 plus 10 over x squared. Now, when we go to take the limit, this portion here will go to infinity. This portion here will go to 0. This portion here will go to 0, and this portion here will go to 0. And so we have the limit, well, we just plugged in the limit. We, in the end, have infinity over 1, which is just going to be infinity. If we wanted to take the limit as x approached negative infinity of this same thing, we'll eventually algebraically get back to here. So we'll have 7x minus 6 over x plus 3 over x squared divided by 1 plus 10 over x squared. And for most of the places, we'll have the same thing. This will become 0 again. This will become 0 again. This will become 0 again. The big thing that'll change is this will now be negative infinity, which means that we'll end up with negative infinity over 1, which is just negative infinity. Alright, so that means, since we know what we have, we can use this to plug in what we're going to end up getting. So we want to look at the limit as x approaches infinity of g of x, which is this function up here, and the limit as x approaches negative infinity of g of x. Now we know from doing our limits of the inside that as we go to infinity, this will be the arctan of positive infinity. Whoops, got ahead of myself. And as we approach negative infinity, this will be the arctan of negative infinity. Now, arctan's a bit of a tricky one to figure out. Essentially, what we're saying is what values are going to give us positive and negative infinity when we plug them in as far as angles go. So if you know anything about the unit circle, a little bit of a side note on the unit circle, just for remembrance sake. If we have a point on the unit circle, we have 1 as our radius, and the point on the circle will be the cosine of whatever the angle is for the x-coordinate, and the sine of whatever the angle is for the y-coordinate. Tangent is going to be the sine divided by the cosine of the angle. So if we want to figure out what we have to plug in order to get positive or negative infinity, what we're really looking at is how do we get the cosine, the denominator, to be 0 and have the whole thing be positive. So if we take sine divided by cosine, cosine will be 0 over here at pi over 2 when the angle is pi over 2. But it also will be 0 here at negative pi over 2. Now the reason that I'm putting the pi over 2 with the arctan of infinity is because the sign here will be positive. So when we get to pi over 2, we have a very small number dividing a positive number. So that's why we'll get the positive infinity there. And when we go down here to negative pi over 2, we'll be divided by 0 again, but sine will be negative here because sine are the y values, so we end up getting something negative, and so we end up having negative pi over 2. Now another thing to note is that when you're talking about the arctangent will only put things out from this half of the unit circle in values. So this is something that we have to keep in mind when we're talking about the arctangent, is it'll only deal with the first and fourth quadrants and what potential angles we could have there. Otherwise, it's ignoring them. And we aren't even dealing with the fourth quadrant from a standpoint of 3 pi over 2 to 2 pi. We're dealing with the negative of the first quadrant. So these will be our horizontal asymptotes. And if we wanted to go ahead and see what the arctangent's graph looked like, so this is the arctan of x. Then we're only looking at values between pi over 2 and negative pi over 2. So this will be negative pi over 2. This will be pi over 2. Should be going through there. This line should be going through here as well. And so when we go to graph, we got this nice 0 point here. And we're getting as close as we can be to pi over 2 as we get larger and larger and larger with our fraction. And as we get smaller and smaller and smaller, we approach negative pi over 2. So as sine over cosine gets bigger, because cosine is getting closer to 0, we're going towards pi over 2. But if we've got a negative value for sine and we're getting cosine to be smaller and smaller and smaller, we're going to negative pi over 2. So these limits at infinity can help you kind of talk about the end behavior of the graph, what they're looking at. In the next video, we're actually going to start taking a lot of things we've been looking at in this chapter and combining them together in order to actually sketch the full graph of a curve.